Welcome all. This is a quick introduction of where we stopped last time. We talked about the pre-processing of the data. This video will be considered as the last video for Unit 2, and I would like you really to concentrate on many aspects that I'm gonna go through like briefly, but we're gonna face them again over and over through the applications and through the categorization of those topics during this semester. However, they are very important, and I would like you to try to read the chapter 2 in details, but not to memorize it. So it's a skimming type, but reading it, not just ignoring some of the concept that is mentioned there. However, as I always say, I rely on the video lectures that I provide, so most of your questions, if related to the chapters, will be mentioned inside the video lectures, and whatever else will be external materials, you never saw it either in the chapters or in the videos. So just a hint of the way that this course is gonna go through the semester. We talked about a little bit about the aggregation, which is one kind of pre-processing the data, and why we do pre-processing. Actually, because our data might be huge data and has a lot of attributes, and we would like to somehow simplify the data and make it easier for us so our application will be able to handle it. So let us just go briefly about the aggregation, which is one type of reducing our data. And for example, we talked about reducing the number of the attribute in the data. We gave this example about moving from city to region to state to country, so make it less representative. Maybe we aggregate data tends to have less variability. Yes, this is true, just to make the data more stable when we don't have a lot of variability in the data, like for example this example above. And another example about the variability, if you take the data as monthly perspective data, you will see a lot of variation in your data here. And we talked a little bit about that, where this one we can consider it as normally skewed data if you consider the yearly base. So this is a quick overview about the aggregation. The second type of reduction is the sampling, and I would like just to mention for those of you who previously had some experience in statistics, this is different than statistic. Sampling in statistics means that you take a sample of data and you apply your statistical analysis on it because you are not able to gather the whole data. For example, let's say that you wanna give an approximate number of the average height of the man in the United States. So you will need to gather all the data, which is the heights of every individual in the United States, which is impossible. That's why you go and you measure the height of sample of your data, let's say 100,000, and then you assume the average that you come up with, that this is representative enough to say that this number represents the average man of the United States. This is in statistic. Whereas in data mining, our data, as example, is, let's say you have Walmart database about the transactions. You have the whole data, but really your software is not capable of running the whole data. So you want to take some sample of this data that is representative and it's good enough, and to run your analysis on it and to come with some kind of analysis to say, okay, I found this pattern in the data, and accordingly I can assume that this will apply for all the data. So it's more to for the overload that you or the overhead that you can have on using all the data, and the expense of the data and the time that you can face when you are using the whole data. You are using the sampling technique, and there are different kind of sampling technique that you can use, and Also, if you read it in the chapter, it has more information about what kind of sampling techniques that and how they are applied. We can mention it quickly. Maybe you randomly select some of by applying some kind of probability, you select a particular item. Or maybe you sample the data without replacing. That means you take the data and remove it completely from your from your data. Some other technique which is with replacement, that means you keep the data. That means it might appear more than one time that you pick the same data in your sample. Stratified sampling, which is more used and more known, that you can split your data for several partitions, then draw random sample from each partition. This way, most of your data is representative, so you are not really ignoring any type of the data. I'll give you an example. Yeah, this let's say that you have clusters of food types. Maybe each one of those clusters represents some kind of food. In this one I have, let's say, 4 items. This one I have 5 items. This one maybe I have 10. And this one I may have a 20, and this one I have a 50. Now if I go and take 1 from here, and I take 3 from here, and I take 2 from here, and then I take 5 from here and 2 from here, actually I represented every group of this data, but my grouping was not equally representative. So the best way is to do, let's use some technique even after partitioning and taking the samples. Maybe let's say from each type of those group, let's take the half of the data, or maybe just 10% of the data. In this way, at least you are sticking to the same distribution that the original data, the whole data has. Okay, and we'll see some kind of this analysis. Okay, we might face problems with the sampling, of course, because sometimes we may lose important information in our data. So let's say I have this this visual picture that can be clustered in many different clusters, and these figures represent 8,000 points. So the resolution gave me this figure that shows 8,000 points on this figure. I can say that, okay, I can look and see that this data is one cluster, if you look at it in this way, and this data is another cluster, and that one here is another one, and here is another one, and here another cluster, and here is another cluster. So this is the real data somehow, and I was able to split it to 1, 2, 3, 4, 5, 6 clusters, 6 different grouping clusters. If I look at this data, which is only representing the same data but with 2,000 points, I still do the same. I can still recognize, and my software, if I run it, it still can be able to find the cluster 1 and the cluster 2 and the 3 and the 4 and the 5th and the 6th. So somehow I preserved the original data by moving to a reduced data set that I can handle it good enough, and my software will be able to cluster this data in those particular 6 groups. However, if I reduce the data to 500 points, as you can see here, maybe I can say this is 1, and this is 2, and this is 3, and maybe this is a 4. Really, I lost the representation of the original data. I lost the quality of the original data. So you have to know where to stop and to which level of reduction you have to go. And the visualization in some tools, in some applications, can help you to do that. Very known topic is the curse of dimensionality. If you have a lot of attributes, your application is really very difficult to be handled. As you can see, the difficulty of as much as number of dimensions, and here each dimension you consider is attributes. Like here I have 50 attributes. For the picture, for example, I have the color, one attribute, the shape, one attribute, the shadow, one attribute could be the blurredness is one attribute, the resolution one attribute, etc. So if I am taking all the attributes under consideration, I am faced by a very popular problem that even I will not be able, if we read this in details, I will not be really able even to find the real patterns in my data because of the difficulties to find pattern in the data when it's really huge. So the main idea is you have to find a way to reduce the dimensionality of your data to be able to analyze it. Very popular algorithms in data mining and famous. One of them is a principal component analysis, and the second one is a singular value decomposition. And each one relies on some kind of algorithms and some linearity functions that can be used to reduce the data. And we're going to see how this works. Another type is supervised and nonlinear techniques. Always when I say supervised, remember the classification. That means there is a class. So if you remember the data set that talk about if a person can cheat on his taxes or not, so the class about the cheating, yes or no, that's a classification. You know the label. You have a supervised learning. Clustering is a kind of unsupervised learning because you really don't know the class. You cluster until you end up in totally some kind of groups, and then you give the name or the label to these groups. One way of, as I said, about reducing dimensionality is a principal component analysis, is to reduce, for example, here I am in two-dimension space, okay, and I use something that the principal component analysis rely on, which is the projection of the data. So I end up looking at the data and I say, okay, is this data, of course, each point can be represented by x1 and x2, but how about finding another projection, which is here the E, that also I can project my data on this only one space and still be able to understand the data. So instead of having two dimensions, now I am moving to one dimension. And this is how it does. Actually, if you have 50 attributes, you go from 50 to see if I move to 49 attributes to 48, etc., until I end up to 3 maybe dimension. And in this way, I can really visualize the data and understand the data. And sometimes it's based on the algorithms, the correlation between the data, and we're going to see that, and that can help me to know which attribute to get rid of it, which attribute to keep, and why there's a reason behind it. So the whole idea is finding the eigenvector and the covariance matrix of the covariance matrix, and we're going to see how we can define the covariance matrix. Another example here, we are in 3 dimension. However, we were able, using the Eismo map also for a kind of reduction, to move to 2 dimensions. So I was able to draw this one. You can consider it as if only in this space, 2 dimension space. So the dips, I am ignoring the dips of this data. It does not exist anymore. So only this blue lines became for me by finding each pair of points that is finding the shortest path distance between them, and I'm ending up in 2 dimensions instead of 3 dimensions. What kind of drawback by using the reduction? It's based on your purpose of using the reduction or your goal. For example, last week, if you heard about the story, the girl in University of Louisville that was kidnapped, they found a photo images about her arguing with a couple of men in the hallway, and they took those photos now, and I know the university, my colleagues are working on finding match of the picture of the man that she was arguing with the database that they have in the with the FBI in the computer forensic lab to find a match. So this is one example. Why would you use a reduction? So really, you have a huge database, for example, of images of people, and you would like to identify those people, 100,000 or million of images, and you got the you had the photo of that of these men, and you are trying to map this photo with the database that you have of images. Now, if you have a huge amount of images, your computer will not be able to find the real match in split of second. Like, it's not like CSI movie that really is so quick, like in one day they can find it. Usually sometimes will run weeks and months if you are running the whole database. That's why sometimes you have to reduce the dimensionality to be able, as much as the picture is good enough to match the original pictures that I have with the database. So for example, this is the pictures that has 206 attributes. So let's say some of these attributes is the colors, the second is the brightness, the third is the shape, the fourth could be maybe the origin, like they categorize them based on the origin of the person, etc. So it has a lot of attributes, or what we said here, dimensionality. If you reduce it to 160, you can still see the picture is reasonable. Even to 120, you can recognize the person. To the 80, you can recognize it. Even to the 40, you can recognize it, and this will speed up the process of the matching. Whereas if I can see it in dimension in 10 attributes, it's really, I lost the information, and very difficult for me to map the picture. However, it's good enough to start from here, and maybe in one day to be able to match all the pictures are close to here, then to go up. So this is the concept of reduction. Sometimes you go down with the dimensionality, and then you go back to the original data if you are able, if you found a match, okay, or groups of matches. And let me hold this one temporarily to be able to move. Okay. Feature subset selection. Let's see if we didn't lose anything. No. Okay, so another type of reduction is to pick subset of those of this data, and it's another way of dimensionality reduction, either by finding duplicates, so you get rid of the duplicate, or something is not important like the price and the tax paid. We know the tax paid is a percentage of the price, so you can get rid of it. It's really, you don't need it. Relevant features based on what kind of pattern you are looking at. So some of them are not important at the time of you are finding the patterns of the data. An example is the student ID is not important when you are looking for predicting the student GPA. Is really not important in your data, so you get rid of it. You don't need some overhead in your data when you run the data algorithms. Some of those algorithms, they use a brute force. That means like random. You keep you run your data and you keep trying. Okay, let me pick 10 out of 100 and see what the result will come up. Then I pick another 10 randomly, another 10 randomly, until I find the best fit that I can really see the data and see some kind of pattern in my data. It's time consuming, of course, but sometimes it works. Okay, embedded approach. It's naturally as part of the data mining algorithm, so you can have this algorithm selection. So you think about it as application, a software that it has this feature embedded approach. It goes and it tries to find which features to be selected that are really naturally to be getting rid of it. As we say, the student ID. Filter approach, you are the one filtering the data. Maybe in your data, the current data you are working on, partly one, for example, the transaction of Walmart. You maybe want to know what is, you don't need the whole transactions of Walmart if you want to just look at the food section. So you get rid of all the other type of attributes that talks about the hardware part of the store. And etc. It's based on what kind of analysis you're gonna deal or you're gonna run on the data. Wrapper approach, and which is you consider it as a black box. You don't know what you're doing. Is very similar to the brute force. You just apply it, and then you will see what kind of analysis, what kind of pattern you can discover, and then you keep repeating it until you find the best one. Okay, so as we talked about the eigenvector that can provide us with mapping from 2 dimension to 1 dimension, or from 3 dimension to 2 dimension, etc. So you are moving your attributes, you're capturing the information from 1 dimension into another dimension, and you're extracting the features. And here the domain expertise needed to know what I am really doing in my data. So it's very important before you run any algorithm to start first understanding the data. Look very deep in the data, understand. You may visually, by looking at the numbers or running the visualization first and look at the data, understand what kind of information I can draw from this information, from this data. As we said, mapping it to a different space, and then maybe combining some features, as we saw when we combined the city to the country regions, and or the zip code with the address, all combined together for one feature if they are split in our data. The concept of discretizations is very, very important concept, so please try to read this information. It is in chapter 2, in page 62 actually, and 63 in more details. There is a concept about the entropy-based approach. Entropy is the opposite of purity. When you are trying to find clusters of data, like you want to, let's say I have these data points and I want to group them. Visually, if I look at this data, I will say, okay, I have here 4 groups. This is one group, second group, third group, and fourth group. So how can I assume that this is right or wrong? There is a measure, which is the entropy, which is the error, how much error in my analysis, and it's a measure based, and the application provided for you. So you can look at the entropy, and if the entropy is very high, you will say, no, I'm gonna try again and find a better grouping algorithm, and you keep running the data until you find the best grouping algorithm. Now, for example, here what they did, they defined 3 categories for both X and Y. So, for example, here, as you can see, less than 1 is one category, between 1 and 4 another category, and bigger than 4 is a third one. The other one is less than 1 is one category, between 1 and 2 is another category, and bigger than 2 is a third category. So they ended up with this data. As you can see, this is one group, so there is no split in them. This is the second group of data, and this is the third group of data, B. And here I can see there is another 2 groups. Here they decided to have it 5. So it's based on you how much your entropy value was when you run those algorithms. Accordingly, you will decide which one of those 2 data set samples that you're going to use. So here, for example, I have 5, less than 1, between 2 and 3, this is the second, between 3 and 4 is third. So less than 1, 1, 2, 3, and 4. So less than 1, between 2 and 3, between 3 and 4, and bigger than 4. Okay. Whereas in the Y, if I am taking, for example, less than 1, between 1 and 2, between 2 and 3, and between 3 and 4, and between 4 and 5. And here I could say not between 1 and 2. So here they can see they ended up with here one cluster, I would say, second, third, fourth, and fifth, and sixth, 7, 8, 9, and 10. So maybe I ended up with 10 clusters. So it's based on what the entropy measure that gonna come up. We're gonna see this in very soon. Another kind as we said, like there's a different kind of method to use discretizations. One of them, like this is our original data, equal interval. They just decided that every 5, every time x equal to 5 and up, let's split the data. So from 0 to 5, from 5 to 10, from 10 to 5, from 15 to 20. And as you can see, they ended up with here, let's say maybe one cluster. This is the second cluster, and this is the third cluster. And as you can see, it's not accurate. Equal frequency, they said, okay, what mean the equal frequency? The number of points. So they ended up with one cluster, second cluster, 2 and 3. K-means is one of the most popular algorithm that is used for clustering the data, and K is unknown at the beginning, so you keep running the data. K is a number, so it could be, let's say I want 2 clusters, so I will name it 2 means. I want 3 clusters, so I want 3 means. So in this case you have a 3 actually. So your data, you will say this is the cluster first one, which is before the 7 almost. This is the second data, okay, clusters, which is between 7 and 9, and this is the third, and this is the fourth. And as you can see, is almost the best clustering for this data. If you look well to the original data and compare it to the K-means. K-means always work very well, and it's very easy algorithm to be found, and we're gonna go over it in future. Transformation is very known kind of transforming the data from ranges into one simplistic model. Usually when you have nominal or ordinal data, you try to use intervals in those data and to convert them to be able to have similarity between all the data to be able to run your algorithm. Some algorithm cannot run if you don't do transformation, that's such kind of standardization or normalization. And a lot of functions can be used to do that. And it's very typical, and we're going to look at it in our applications. Now, similarity and dissimilarity. So the similarity between, you say, okay, I have 2 points in this space and they are similar to each other if they fall, if they are both similar, then I will say both of them equal to 1. If they are not similar, I will say they are 0. So, and they are falling into the range 0 to 1. Now, if my data is not from 0 to 1, there is a technique that you can use, as we say, the standardization, that you can, and you can read it also in, I think, in pages between 66, 67, and up, and 68. You can see how you can do the interval. For example, if your data is 0, 1, 2, 3 until 10, this is your data, and you want just to have the interval between 0 and 1. So actually what you say, okay, the lowest number of my data is 0, the highest is 10, so I will divide all my data, this is a A and this is a B, so I will divide all my data over B minus A, which is equal to 10. So in this case, you'll end up 0, then 1 over 10, 0.1, 0.2, etc. So the biggest number will be 1. So actually you have this interval 0 to 1, the range will be. Usually it's always positive, the similarity. This similarity, just the opposite, if two objects are not similar, so we'll say the similarity between them is 1, because they are not similar. So opposite concept, and they are because we are looking at the dissimilarity, and they are and if it was 0, that means they are similar. So, and usually also is between 0 and 1, or could be go from 0 to infinity. It's based on the measurement that you want to follow. And this is very typical way of transforming your data. So if you have either nominal data or ordinal or interval data, you may say, okay, they are dissimilar if both of them equal to each other, so 0. If they are not equal to each other, so they are 1. So the dissimilarity 1. In this case, similarity, they are similar to each other, so I will give 1. Just it's like a concept applied. And as you can see, the S is the complement of D in this case. For the ordinal data, you can apply as we did previously, as you saw with the example from 0 to 10. If for each data point you take you negate the 2 points, and you divide it over the number of objects minus 1. Or you can measure the similarity, which is a complement of the similarity 1 minus this value. For the interval, you can use just the absolute value of the first object minus the second object, or the other kind of normalization that you can apply on. And it's up to you which one of those you can use. And we're gonna see it, it's built in. We're not gonna use it manually, we're gonna see it in our applications. One of the most popular measurement of similarity between items is Euclidean distance. Euclidean distance is very popular, and it's used in many type of data, and it's known because the computational aspect of using it is very small, so really your application will not have any overhead when you are using it. And most of the application we really rely on the Euclidean distance, and we're going to describe it now shortly. So the Euclidean distance can be considered as approximation for the continuous attribute of the data, and it's very used, especially between objects. If you're gonna see, like if you are measuring the matrix between objects, this is the best way. Is not very typical to be used in documents, for example. It's more for transactional and for matrix data and records, and we're gonna see how we can apply it. So the distance between any element, it's between any two objects, it's equal to the sum to the differences between those 2 points squared, and then taking the square root of the all sum of those objects. And we can see it in practice now. So for example, let's say we have those points, which is a different point, P1, P2, P3, P4. And I would like to measure the Euclidean distance of each point between those points. Of course, each point with itself is equal to 0. If you apply the algorithm, you can see that it is. Let's go back. So actually, you are taking off the same element, so the output will be 0. And let us go back a bit here. Where if you want to calculate, for example, between P1 and P2, so you are taking the x's and the y's, so you are saying the x, y equal to, so let us bring the original equation, like the square root of the sum, okay, equal to 1 to n to xk minus yk squared. So let's calculate it here. So you will say 0 minus 2 square, this is the square root, plus 2 minus 0 square, and this is equal square root, this is 4 plus 4, and in this case this is equal to the square root to 8, which is equal to 2.828, which is the first number that we have here. Okay, in this case the other number here, the same, it's between P2 and P3, so 2 and 3. So what you do, 2 minus 3, we take the square, plus, so 2 and 3, 0 and 1, 0 minus 1 square, and this is their square root, and this is equal, so we have 1 plus 1 and square root to 2, which is equal to 1.414, which is this one here. And as you can see, the matrix is symmetric, and any 2 point is a symmetry, and you can see the equivalence of the both side, and this is typical features in Euclidean distance. Very simple technique. The second, so this is the Minkowski distance, which is applied for the all. Like if you substitute the r by 2, you end up with Euclidean distance. Is substituted by 1, you get the Hamming distance, which is Manhattan distance also is named, or the Bloch distance. If you go to the infinity, you end up with the most popular function, which is supremum, which is you get the highest, the biggest number, and we're gonna see it very easily here if you wanna see the result. So the first one, this is the Euclidean. Here is the Bloch. This is the easiest one, which is you take actually in this case r equal to the 1. So for example, dx y equal to the sum of, let's say I am calculating P1 and P2. Okay, just to give you an example, P1 and P2. In this case, what you're saying, give me the absolute value between 0 minus 2 plus the absolute value to 2 minus 0. In this case, this is equal, this is the absolute value, so I have here 2 plus 2, which is equal to the 4, and I was able to get this number here. And another example, let's say I want to calculate between 4 and 1, so between the 4 and 1, so 0 minus 5, absolute value, so it's 5, 2 minus 1, it's 1, so B is equal to 6. Now the last one, which is the most unused one, which is the Superman. In this one, what you do, you take the highest number. So for example, you let it go to the infinity. So you will say the distance equal to, you let it go to the infinity, but I will simplify it for you. Let's say I'm using 1 and 2. Okay, 1 and 2. So I should be able to end up with this number. So between 1 and 2, you will say, okay, 0 minus 2, the absolute value that it goes to the infinity, and plus 2 minus 0, which is goes to the infinity. Then all of them will go over 1 over the infinity. Okay, in this case, I would say here, since the absolute, 2 is over the absolute and 2 over the absolute, which one is biggest? In this case, both of them equal, so I pick the 2. To give you a more reasonable example, let's say how we found the 5, so 1 and 4. So let's consider the 1 and 4. So 0 minus 5, okay, plus 2 minus 1 to infinity. So this one goes to 5, absolute value, plus, of course, all of it will go to 1 over infinity, plus 1 here with infinity over infinity. So which one is the biggest? Is the 5, so I will get the 5. So this is very simple description of those distance. The most famous, I will go back and say, is the Euclidean distance, and it works not because it's famous, but because it works the best, especially in the clustering algorithms, and even in categorization. It's very, very famous. Now, another concept, which is Mahalanobis distance. In this one, you are trying to find the inverse covariance of the matrix, and as you can see, I have 2 points here, extreme 2 points, this one and this one, and you can see there is a correlation between the point. Those points can be linearly correlated, and this is a problem usually happens. So if you are using the Euclidean distance, you end up with this number, but if you use the Mahalanobis using this equation, you end up with 6. So it's recommended to use it when you have a correlation between your attributes. So you try to derive yourself from the Euclidean distance only when you find in your data, if you run correlation at the beginning of your data, you will find if there is a correlation, I will go and use a different kind of method to measure the distance between the objects in my data. Let me see if I have, so this is a very simple covariance matrix between ABC point. Let's see if I have examples of the covariance here. It's mentioned in the book. Okay, so you can look at it in your book on page, after the Euclidean, the similarity, you can look at it in page 77. So the correlation actually is you are looking at the correlation between 2 points, and to find it is you have to first to find the covariance, which is given by the sum of the points, as we did we negated the 2 points, the x's and y's, we multiply them in this case, and we got the sum on them, and then we divide them on the number of points minus 1. So we do this for the covariance. Then we find the standard deviation for each dimension. In case of the x, we find the standard deviation, which is the square root of 1 over the number of items minus 1, and I don't want you to memorize the sum of each point minus the mean of the data for each attribute. The x you calculate it alone, the y you calculate it alone, and then you multiply them together, the standard deviation, and you divide the covariance on that multiplication, and you can find the correlation. As I said, in our application, this will be made for you. You don't have to make it manually. You just, when we need to run correlation, you just pick the correlation and you apply it. And there are very interesting examples in page 77. You can see it's very easy. Just follow the numbers and just sum up, and you will find it very easy to understand. And if I don't mention them here in detail, that means you don't have to worry about them, as you're not going to be asked about, but I would like you to read them. What are the most common properties in the Euclidean distance? Very, very famous things, that if distance between 2 points is bigger or equal to 0 for all P and Q and D, that means and the distance between the two points equals 0 only if P equal to K, and this is what they name it as a positive definitions. And the other concept is symmetry, as we saw it in our data, how it's equal like if the distance between P and Q is equal to the distance between Q and P, and that's why we ended up when we calculated the correlation between the point and itself, it ended up equivalent distance between a point and itself, it ended up with 0. And this is the most powerful formulas. That this is one of the properties that you know, that this is an equivalent distance between 2 points, the triangle inequality. So if the distance between point P and R should be less than if you are going from P to Q and then going from Q to R. So this is very normal. And so the distance that satisfies these properties is known as a metric. What else that properties of similarity? We thought this in the table actually. So similarity between 2 points P and Q is equal to 1, or the maximum number, measures that we are using in our intervals. And we say if the 2 points that they are symmetry if all the points that in that object that follow the following concept, that the similarity between 2 points P and Q equals similarity to QP if we just interchange those points. For the binary, it's very important that you use some kind of Jaccard coefficient, and this is very useful in two types of data sets. One of them is if you are dealing with transactional data, and the second one with text data. For example, if the way that, as you saw in our second video, the data of text data, they convert them to numbers, and they convert them sometimes to the number of reoccurrence of the text in the number. In the text actually. So how can we use this matrix to help us to find similarity between two texts? For example, let's say I have two texts and I would like to know if those two texts are similar to each other. So the more the number of words are occurring in the two documents, the more that those two documents are similar. So one kind of it, it's known as Jaccard coefficient, and the concept is very simple. Here I only care if the two documents are equivalent. Like for example, in the book, it's very simple example saying like if you have questions of students and the student has to answer yes or false or true. So let's consider this is if the two the answer the question answer was 0 and the student answered it as 0, so this is considered good. And if it was true and the student also answers the question by true, so this is good. I don't care when the student didn't answer the question right. So I only calculate the number of times that the student answered the questions right, and then I divide it on all the questions that I have. In this case, I end up knowing automatically my software will know the grade of that student answering those questions. Now, another type that is very much useful, this is not for the questions type, is more for two texts that if they are matched. As we saw in our data set in the previous video, that if the word is not appearing in the text, will give a value 0. If it appears, give value 1. So I only care if those two words appearing in the two documents. So only this row is important for me. That's why I have a different kind of matching using the same Jaccard coefficient but in a different way. So I only calculate the number of times those words occur in two documents, and I divide them on the number of the word that occur in the document. Of course, I ignore the zeros because zeros mean that they didn't occur at all, so I don't give them any importance in my calculations. This is important also. For example, here the simple also kind of Jaccard example. Let's say that I have a number of attributes of data point P and data point Q. So we'll see how much matches we have. 0 and 1. For example, when we have this case at 0, 1. So as you can see, it's 0 and 1 here. So this is one time and this is the second time. That's why we end up with number 2. 1 0 only we have it one time, and 0 0 most of the rest, so 7 times. 1 1 we never had it, the 2 points equal to 1 1, so we have it as a 0. So if I want to calculate the SMC, I would say, okay, let's calculate how many times that they are. Both of them were 1 and both of them were 0, so this is the similarity between them over the all. In this case, I have the 0 and I have the 7, so 7 over the total, which is 10, which is 0.7. Now, if I am considering the second type of example of Jacquard, which is I'm concerned about matching two texts. In this case, I only care about the two texts appearing. So this is more for the transactional concept, or for the question kind, true, false questions. Here is more for two words appear in two documents, or words that the same words appear in two different documents. So I'm only matching those words. In this case, I have 0 here, and whatever the other values that I have, so I end up 0. So those two documents are not similar to each other at all. The other very important concept is the cosine similarity metric, and this is very used in the documents, because if you have, let's say I am in two-dimensional space, and I have document 1, their attributes represented as the following. Okay, and I have a document 2, it's represented like this. So each point of those, it's represented by X and Y. So this is the vector for document 1, and this is for document 2. Those documents are how much similar to each other is based on the cosine, theta, the angle between those two documents. If there's those two documents, let's say the following: if those two documents were 1 and the other one was on top of it exactly, I will so theta here equals 0. Those two documents are exactly the same, and those are as features. So the document is represented as attributes. Okay, so this is, let's say, the first as a vector space. The document 1 represented by those numbers, the document 2 represented by this number. So to calculate the cosine of two documents, first of all, you get the dot product of the two documents, and we'll see how. And we divide it on the length of the first document multiplied by the length of the second document, because this is very important. Let's say I am using Google search engine, and I am searching for the word Western Kentucky University, and I have one document that mentions Western Kentucky University 10 times, but this document has about 10,000 words. And I have another document that mentioned Western Kentucky University 3 times, but it has only 100 words. So which one is more important? Of course, the one that has only 3 times, even it's not 10, but because the number of total words in that document is 100 words, which is smaller. So that's why this is the kind of normalization that we talked about previously. Here we can see it more in document, because we deal more with documents and we are far from the numerical numbers. So here you can understand why we have to standardize somehow and normalize our data. So how you can end up, if I give you something like this in the exam, how you can calculate it. I give you the first document, I give you the second document. What you do, you calculate the dot product. So you get 3 multiplied by 1, so you consider it as column 2 plus 2 multiplied by 1. So we are getting the dot product. 0 by 0, 5 by 0, 0 by 0, 0 by 0. So consider like this: 0 by 0, 2 by 1, 0 by 0, 0 by 2, and you sum them all and you end up with number 5. Now to calculate the length of D1, what you do, you are multiplying each attribute by itself. 3 by 3 plus 2 by 2, 0 by 0 to the end. The same for the second document, 1 by 1 plus 0 by 0, 0 by 0, 0 by 0, 0 by 0, until 2 by 2, as you can see here. And you take the square root of this one and square root of the previous one, okay, and you end up with those two values. Okay, and the cosine similarity will be you are dividing the dot product, which is a 5, over the multiplication of those two, and you end up with the number 0.3150. And also you can see the example mentioned in your book. However, I think I explained it well enough here on page 75. Okay, another type of Jaccard coefficient, which is extension of Jaccard to reduce attributes, also is known for the binary attribute. I'm not gonna go in details about this one. We're gonna see it during the semester. Correlation, we went a little bit before. We talked about it. First, we have to standardize. We have to use a standard deviation. And then we can calculate the correlation by using the covariance and dividing the covariance over the standard deviation. And you can go to page 77, as I said before, and you can look at it. It's very simple, and it has an example with it that you can look at it. What else? The general approach of combining similarity, it's known like to do that you have to, if you have case attribute, you compute the similarity and you put them into range because you did some kind of normalization. You have interval between 0 and 1. And then for the delta, you will say it's a 0 if they are missing value, otherwise it's equal to the 1. And you compute the similarity between two objects using the following: similarity between both equal to sum to the multiplication between those two values over the sum of this specific value. We're gonna see it in more details in future. This is important concept of the weight, because sometimes your data has different attributes and different importance of each attribute than the other. So in this case, you add the weight on your each attribute, and this weight will be different for different attributes. So it's not so far from what we saw before. Only the difference is we are when we are calculating, let's say, the Euclidean distance, we are considering the weight of each point, and the weight is distributed differently based on the kind of attribute that you are calculating the distance between. For example, if you are having a data set that it has the age of the people, this is an example given in the book, and the salary, you give more weight when you are calculating the distance to the salary than the age of the person. You consider the age, but the weight, maybe you will say, okay, I will consider 0.7 as a weight for when I am considering the attribute of the salary, where I will give 0.2 when I am talking about the age. And that will be given, and with the experience working with the data, you will be able to find this. The density, based clustering require a notion of density, and this is we're gonna see it more also in the clustering. So when we talk about the Euclidean density, which means the number of points per unit for volume, so how much number of points I have really in my data. There is another concept which is a probability density, and there is a graph-based density, very popular, and you can investigate them. So the Euclidean distance, which is cell-based, you can see from looking at the data here, if I'm looking at the metric here, you can by yourself distinguish between those zeros that I have this cluster here and this cluster here, and you can see the mapping, how it ended up with this kind of density function. Euclidean density is a number of points within a specified radius of the point. So here in this case, we decided like we need the radius to be in this specific measure, so all those points that outside this measure are not part of that cluster. So we are, this is our centroid, and the centroid decided by the radius how many points will be included. If my radius was bigger, let's say like this, in this case all the points will be, see my circle is awful, all the points will be included in that case. And this is the type how actually the clustering works, is based on how big the radius of your clustering. So you may start with a smaller one, and so you end up with a lot of clusters. So as a hierarchy, you will end up, maybe you will end up, you start with the smallest radius that will, each point will be considered one cluster. So 1, 2, 3, 5, 6, 7, 8, 9 points in this case. Then what you say, okay, if the distance between the 2 points is equal to this specific amount, let's merge them. So those two will be merged together, and after next step, iterative function, you will say if the distance is a little bit bigger, so you will see like you merge those together and you merge maybe those together. Your algorithm will do this and merge those together, and this is stay alone, this is stay alone. You increase your radius a little bit bigger, and then what will happen if it is in this distance, your cluster will become that one, and those will be excluded from your group. This is how we ended up to the first slide that we saw previously. This is about 1 hour so far, and I think this is our last video. And if you have questions, email me, and I'll be more than happy to answer your questions. You will have the answers for chapter 1 and chapter 2 questions added to Blackboard. And see you in unit 3. You will have the lectures posted, and afterward you will see the video tutorials posted too.